Here we have a op-amp circuit. Notice that we have an op-amp. Notice that we have a connection here, a feedback connection between the output and the inverting terminal. This is going to give us negative feedback, which is going to make sure that the op-amp remains in the linear region. We have voltages at the two different terminals relative to the ground here, and so all of these we can imagine are connected to our reference node. And we're interested in what the output voltage is. We're being asked about the output voltage when we have various input voltages here. Now notice that we have, if we call this ground, we have a voltage difference VB here at this node. Since we are in the linear region, we know that this other node has to be VB as well, because the two input terminals of a op-amp in the linear region are going to have the same voltage. We also know that if we want to count the currents flowing into the two terminals here, those two currents are going to be zero. That we have very large input resistances for the two input terminals for the op-amp, so we don't have to worry about the current there. If we want to compare the output voltage to the input voltages, we're going to have to do a KCL equation here. We have this node where we know what the voltage is due to the connection through the op-amp. We have some currents flowing into that node, and so we can write a KCL equation that will compare and relate these inputs to that output. Once we have the KCL equation, we will write the currents in terms of voltage differences and resistances. By Ohm's law, the current is the voltage difference divided by the resistance. For the first question that we're being asked, we want to find VO, the output voltage, if VA is 1 and VB is 0. So if we are fixing these values where this is 1 and this is 0 and this is 0, we're trying to find V out, and in fact here we can see that V out is the only unknown in this equation. And so we can simplify that. So we found out what VO is. We found it to be negative 4 volts, and then we always want to check negative 4 volts is between positive 10 and negative 10, so that is in the linear region, which was the assumption we made when we did our calculations. So this is the answer to part A. For part B, we're asked to solve the same equation, but we have different values of VA and VB. And so what we can do there is go back to the same original equation and plug in the new values. We haven't changed the circuit at all, so we have the same currents flowing, we have the same expression, but now for the second part, we're trying to find VO when we have two different values of VA and VB, and so we can plug in those values as well. And so we can do some algebra and solve again for VO. Here we can simplify, and then we'll move the 2 over, and we find that VO is equal to positive 6 volts in this case. Again, we check, plus 6 is between negative 10 and 10, so we are in the linear region still. So we're getting a reasonable value for V out. The last part, we're being asked to specify the range of VB that avoids amplifier saturation. So what that means is we want a range of values of VB. Amplifier saturation occurs when the output voltage tries to go past the supply voltages. So the limitation here is that VO has to be between negative 10 and 10. And so in this case here, we want to find the range of VB, so that means we want to leave VB as a variable in this case to solve. So again, we'll go back to the same equation. It hasn't changed because the circuit hasn't changed, but we're going to leave VB as a variable. So in this case, we want to leave VB as a variable, and we want to figure out what range it's going to be based on the limitation that we know the limits on VO, because VO is limited by the supply voltages. So what we'll actually do here is let's leave this whole thing algebraically. We'll see that if we leave this algebraically and solve this as a single algebraic equation, we could have gotten these solutions as well. So I'm going to multiply through by 100k first. So that'll cancel there, and we'll get a factor of 4. And what we end up with here is VO is equal to negative 4VA, because the positive value here becomes negative as it goes across the equal sign. I've got negative 4 and negative 1. That's negative 5 VB. That negative 5 becomes positive when I move that across the equal sign. So I have an algebraic equation for VO, depending on VA and VB, and in fact, if we plug in the values we have here, we get that value. If we plug in the values we get there, we get that value as well. So we could have done this at the beginning if we wanted to. We want VA to be 1.5, and we want to find the range of VB to avoid saturation. Well, to avoid saturation, that means that this output voltage has to be between the supply voltages that are plus or minus 10 volts. So we can look here, negative 4 times 1.5. This term right here is a negative 6. I can add negative 6 to both sides, and I'm going to end up with, I can add negative 6 to each term. Negative 10 plus 6 is going to give me 4. When I add 6, it's going to eliminate that term in the middle, and when I add 6 to the other side, I'll get 16. And so then when I divide through by 5, I have a range of values now that VB can be. And as long as VB is in this range, it means that VO is in that range, which means we're in the linear region, and we are avoiding saturation in that case.